Thank you, and thanks to Joan for volunteering me as usual. Joan rang me and she said we was doing this bit about academic research, and I was like, Joan, you're speaking to me. Not very intelligent, but then I had to think about it. And I've got two projects where actually the Network Rail link with UK RIM, the University Network, and the Manufacturing Technology Centre has helped me unlock a couple of key pieces of innovation. So we're going to present on that. So the first one I wanted to talk about is the mobile wind turbine. Excuse me. So why do we need a mobile wind turbine? Well, it's not the best picture, but all our sites at the moment are powered by diesel generators, and that's not very sustainable. Obviously, fossil fuels, global warming. Also not very good for our line-side neighbours, noise. Most of our welfare setups are literally by people's houses, so anything we can do to be quiet is a good thing. There's also an awful lot of logistics involved with wet fuels. We've got to refuel them, spills, environmental. There's many reasons other than sustainability is why we want to get rid of diesel generators. But cost is a big driver as well. So what have we done to date? We use solar power. So we've had a couple of successful sites in the summer where we literally run the whole sites, well, 98% of the site, just purely off solar power. Big problem with solar power, the sun doesn't shine that much in the UK. And when you actually look at renewable energies in the UK, 8% of renewable energy is solar power, 30% is actually wind power. So why don't we have a look at wind power? And that led me on to trying to find out if we could do something with wind power to do our sites. So again, I reached out through the technical authority and the link with the UK universities, and led me to the University of Birmingham, where I'm stood here today. And that's where I met this gentleman here, Ben, who I'll introduce in a second. So I'm going to hand you over to Ben Murcott, who basically is the father of the mobile wind turbine.
So good afternoon, everybody. Yes, I'm Ben Murcott from Murcott Energy. I am the director of the business, and we're a business based down in Worcestershire. Our primary product is the transportable wind turbine, and this on the screen here is one of our early prototypes that went through about 18 months worth of testing in Stockton-on-Tees. We serve the rail industry, but also construction and utilities, and then sort of the other half of the business, we do engineering consultancy, namely FEA, and I'll come on to a little bit about that later, how that's kind of helped the wind turbine side of the business too. But we're really focused on innovation, pushing the boundaries of current technology and applications of technology. So, as Nick mentioned, we've been involved with the University of Birmingham multiple occasions over the last sort of 5 to 6 years. The most notable occasion was for the ETETA program, and they were offering about, I think it was 10 hours worth of a professor's time to look at our existing technology, namely our patented gearbox, and how we could develop that technology. There was a limitation we had, and we were scratching our heads, and the guys here helped us progress and advance that technology. And at the time it was TRL 6, or Technology Readiness Level 6, so that's basically the wind turbine had been tested in a relevant environment, but it was yet to be properly tested in a commercial one. And as Nick mentioned, about 3 years ago now, because we've got that relationship with the University of Birmingham, they in fact recommended Murcott Energy to Nick, and then so began that relationship between Murcott Energy and Network Rail, which was obviously fantastic for my business. And then we started this journey of collaboration, and the Network Rail's basic objective, as Nick's described, was to be able to use wind energy to provide a renewable energy source, an alternative to their heavy reliance on diesel generators. So after we went through a long series of design reviews, initial ones, critical design reviews, sorry, I clicked the button there, and that was all about learning about the user requirements, system requirements, and it kind of morphed from from a concept, and it's quite an unusual looking wind turbine, but essentially it needs to be transportable and be deployable and ready to go from arriving on site within 60 minutes. They haven't got the luxury of spending days putting nuts and bolts together had to be very quick and easy for them. So, and it's also at the same time being safe and able to perform. And the target was to be able to produce 10 to 15 kilowatt hours a day. Again, they're trying to reduce reliance on diesel generators and also complement their use of solar panels. And then of course with safety and performance in mind, also there was the commercial side as well, heavily concentrating on that, making sure that this is going to be actually a viable venture for Network Rail. So lastly, so here's the real thing. After much hard work and collaboration together, it's now down in London at a site near to Acton or Ealing, and technology readiness level 7. I'm pushing it to move it to 8, which is basically getting a step closer to full commercialization. It's attached there to a battery storage unit, and we're doing a lot of data monitoring at the moment to really see the performance of the wind turbine, how useful it's going to be, but also how we can further develop that technology to hit those targets. So thank you very much. That's my time talking about our wind turbine. Thank you.
Thanks, Ben. So the second one we're going to talk about is rail warming for stressing. So again, back to the affordability challenge, and also Schedule 8 and causing delays. Critical rail temperatures is one of the biggest risks we have in track renewals. If we have a track buckle, that's catastrophic. And spring and autumn every year, we go to massive lengths in the renewals business not to apply a critical an ESR related with a CRT. So much so, track renewals, where if we had a 400-yard job, we may knock that down to 200 yards just so we can get it welded and stressed in the core. That, we were talking about the affordability, straight away doubles our costs. But it allows us to run the train too. So I wanted to try and find a way of how we could do the stressing on the critical path at the point we put the rail in. And again, this is nothing new. I looked around what everyone else is doing. You go to Germany, you go to Austria, they don't use tensors, they use rail warmers. So, and I also then looked about what the actual CRT are costing us, and I was a little bit surprised actually. It wasn't actually costing us that much. But again, when I looked into it, I spoke to people like Brian and John and stuff like that, it's those efforts we put into not putting a CRT and those reductions in volumes, and actually absolutely huge amounts of money we could save. So again, as I said, I then went around looking for possible solutions. So on the, dyslexic, this side, is the rail warmers. This is similar to what they use in Germany. And again, I think Michael Wiedel is in here. So I know Michael from my high output days. So I had a good chat with Michael about how they go about doing it in Germany. So Michael's been really helpful with this one. And we are actually pursuing the gas heaters, and we're putting that through product approval. But those people who know me, I did a lot of work on induction welding, and I know that how efficient using induction is for warming stuff. So the question was, oh, actually, can I warm the rail using induction as well? And I knew nothing about it. Fortunately, Heather, who works with me at the Manufacturing Technology Centre on induction welding, I thought, I know somebody who could help me with induction warming. So I asked Heather to lend us a hand. So I'm going to introduce you to Heather now, who's going to talk to you about the MTC's work on rail warming. Heather.
Hi everyone. So as mentioned, today I'm speaking on a bit of collaborative work we did this year with Network Rail. This is following previous developments on induction rail warming, and I'll present on the following project for feasibility of conducting induction heating to warm rails and the method we used. Just a quick bit before that, however, I would like to speak a little bit about the MTC, who we are. We're an independent research and technology organisation. We're almost 15 years old. We were actually founded by 3 universities, including the University of Birmingham, Loughborough and Nottingham University. Within the MTC, there's about 1,000 of us, and about 400 engineers. We have a large modelling and simulation team, about 30. And within this, we have wide expertise, and the companies have members who work with us in other domains, bringing in their expertise from other areas. So this is just an illustration to demonstrate where we work, typically between universities, academia, and industry, to fill what we call the Valley of Death and bridge between technology readiness levels 4 to about 8, so just before full production. In this, Network Rail are members of the MTC, and this enables them to work with us specifically on combined goals, where they can gain specific knowledge on applied technology to a particular process. We are in turn able to further develop our modelling capability in this particular case through broader and novel practical application. So in this challenge, rail infrastructure faces increasing challenges from many aspects. We have seasonal changes in ambient temperatures, and this gives substantial forces on the rail, approximately 2 tons per degree Celsius of change, and results in rail expansion and contraction that complicate the installation process. Managing these stresses during installation is crucial to ensure track stability and long-term durability, because of misalignment and buckling issues can lead to costly delays. Currently, there are other alternative heating systems, such as gas ones, which can be used to control track temperature, as mentioned, but this is quite resource intensive and limited in scalability. So for Network Rail, a more efficient, adaptable heating solution was required to address the operational and cost challenges while supporting a sustainable infrastructure. So as mentioned earlier, we've previously modelled induction welding for Network Rail. In this, we simulated joining rails together by welding the ends together with an induction coil and then forging it. So we already had a model that we could use in this new application of raising the initial temperature of the rail. And the benefits of the technology we knew from this are quite clear. It's fast, precise, localized, and safer than most other methods. We wanted to explore the feasibility of heating the rail using this modeling, simulating a coil on each side of the track that moves down, warming it continuously, bringing it up to that average temperature of 30 degrees Celsius. So for this, we created a quarter model that goes down the length of the rail. We cut it in half, and then we cut it in half again across the width. And this takes advantage of the symmetry of the rail, and this is developed in a program called COMSOL, and it enables us to run a quick simulation with suitable accuracy. And the multi-physics nature of this induction problem here is key, which is why it's essential for us to choose the right software and the setup of the model. The initial design is shown here. It had a couple of things that needed tweaking, such as the length of the coil. You can see here it goes almost right down to the ground, and this was seen that it would clash with the clips that hold the rail in place. And also the gap between the coil and the rail head, it wasn't quite large enough initially to prevent local overheating. So what we did was do a second iteration, as you can see here. This is just a little movie to illustrate this. And we added separation from the coil from the head to reduce the change in temperature at the top, and also removed the coil at the foot of the rail in order to clear the clips so that we had sufficient operation. We then calculated the power required from that coil for 2 rail types in order to warm it sufficiently. We looked at the moving aspect of the coil to see what rate we could possibly warm the rail at, and worked out that this required about 24 to 25 kilowatts, depending on the rail type. The modelling suggested that the EM56 rail was feasible to warm with this initial coil design for induction heating, but for the 60, we would need a little more optimization to tailor the coil, and for other rail types, we also need to optimize a little bit. So to surmise, we demonstrated that induction heating is feasible for the 56 rail, and shown that potential successful implementation of raising the rail temperature to 30 degrees average across 200 meters in 45 minutes. Additional development is required, particularly for alternative rail variations, to optimize the heating technology before full deployment. However, the technology shows strong promise for scalable development across applications and industries. In this case, if it's developed and adopted, the yearly saving could be around £750,000 with a return on investment of just 6 months. Thank you.
Thanks, Heather. And just on the 45 minutes, well, it's 260 metres. That is basically the same speed the clippers work at. So the idea is, as the rail's thimbled in, we warm, we clip, job done, we walk away. Again, the wind turbine is at Old Oak Common, so we've got a few little tweaks to doing it, but once it's up and running, we happily invite people down to come and have a look at it. So I'd just like to say thanks to Ben and Heather for supporting me. Thank you.